Also here, maybe the disorder should play some role. Because in a lab, you see, at least with this circuit theory approach, they couple many junctions, and this junction would certainly be very different, one with the next one. And this induces not only on-site so-called disorder, but so here it means that not only the so-called hopping turn will be disordered, but you can add both the hopping and the on-site so-called potential that will be disordered. And this might be nice because it can lead to some Bose-glass phase. But first, let's say that the first goal here is really to build this mode state.
Sorry, may I ask you a follow-up question? So you mentioned that in one dimension, on one side you have essentially spin model, hardcore bosons, right?
Yes.
And on the other side you have regular bosons.
Yes.
So hardcore bosons in 1D is basically fermions.
Yes.
So
here,
you have a...
Yes. Yes.
So is there some point where fermions become a boson, or so how does it happen that you go from one statistics to the other statistics?
Okay. So I can explain like this. So first, you know, we cheat. You could tell me you build this phase boundary, but in a wrong way. Look what we all did before. And we build an order parameter, a superfluid order parameter, which is the expectation value of A. But A is the photon operator. So what we have to do really is to show that what is in a superfluid phase is the Dray state object. So what we have done at a general level, you can build an exact mapping from Jaynes-Cummings. So here it is in our paper, the one that I showed here. So here you can write down an exact mapping between Jaynes-Cummings and Dray state Hamiltonian. And then you get a complicated Hamiltonian, but still, if you are in a 1D and close to that state, you see that things become quite simple because you just have less state. It means that the Dray state, you just keep as a minus branch, because I just told you that you can really ignore the plus branch because they cost higher energy. So here, in 1D, you can look at this Dray state basis and show that here they are hardcore boson. So there you can really nicely map a model of spins in a nice way. In 1D, you just use, tricks of things, in 1D. Now there, things are very difficult. The things we know how to solve is purely no coupling between light and matter. Because as you mentioned here, the main point which is hard here, the A are photons, they are boson. But these sigma, they are spins, they are hardcore boson. Here spin, they don't couple. Okay? So still we could write down spin as fermions. But how do we write down a basis that couple photons and the fermion? Of course, we know how to do that for the nicer case of the Anderson lattice, where we have fermions that couple two spins, right? But here the main thing which is difficult is spin coupled to photons. And therefore, up to now, we don't know much about this field theory. But we agree that if G would be 0, you get a superfluid state of free boson. But now the main point is how do we pass from hardcore boson to free boson? And this, we don't know much about that. Okay? Okay. So, but again here, so we have things to work on, but the main challenge from application point of view, to me, seems how we can really realize it. Okay. Then, next thing that I want to talk about, maybe we don't want to put qubits now, and we want to go to nice things. So what can we do? We can have a new state of matter like here. So this came a few years ago and was based on this very nice idea by Duncan Haldane and Ragu. So the idea is that you heard about this beautiful state of matter that we call is a quantum Hall effect. We apply a B field, and because of this cyclotron force, we open a gap into the bulk, and at the edge we see some modes that just flows around. But then the point was you don't need to have fermions. You can really do that with cold atom bosons and photons. Main point is you want to be in a case where you open a gap into the bulk. So you don't want to have any state into the bulk. And you want to mimic the application of so-called magnetic field. And what does it mean? It means that you just break the time reversal symmetry. And in nature, you can do that in many, many ways. So here there are some ideas to really realize that in a so-called in a way. But here the point is you can use this lattice of rods and light scatter. And main point is, like in the quantum spin Hall phase in 2 dimensions, you want to have Dirac points and open a gap that breaks the time reversal symmetry. And there they have, in this work, they have done it in a very nice way. And they have probes that indeed one can have edge modes of light that can really follow a purely one-dimensional so-called motion and is not backscattered by any impurity. And this is a beautiful work, I think. And here there are groups that have made a very nice idea. So maybe I come back to that because I think it's also a nice so-called proposal. So I need to come back to this paper that here there are some idea which is very nice and claim that you can realize the same idea with a spin-full version where you don't break the time reversal symmetry. But what I would like to do now is to go back to our circuit system and say how can we think in terms of a gauge field that Jan used to play with cold atoms. So here, one idea. So this was Steve idea mainly. So the idea is we could. So now this LLC circuits are waveguide, okay? Because we keep one mode of light, so we can really see that as an LC circuit. Now we want to build in a lab or in our mind. We want to build a junction where photons would hop from one waveguide to another, but would fill a complex phase. So how do we do that? Well, we could play with matter, and matter here is a so-called a superconducting ring with Cooper pairs. And if you apply a flux, the Cooper pairs, they fill the flux. They are charged. So they start to move in a way. Okay? And our main idea, you want to integrate out the ring and prove that it can generate a hopping for photons that would be accompanied with a phase, which is a complex, and which can be tuned with phi, the flux. So, of course, it can work, but it is not simple as it seems. First, you could tell me it could depend on how many junctions you choose. But not only that, we managed to show that it works only in a domain of charging energy of this ring, because we have a small ring, and the Josephson coupling here, which is quite narrow. But still, if you look at this work, the main point was to show that indeed you can induce these complex phases if you play with charging energy and the Josephson coupling of this ring. Okay? So now, let's imagine we can do that. How can we build a very nice phase of the map? So at a general level, we just notice here, and in fact, this is simple. Now let's imagine we start with our waveguide, and now we put a small ring there, and there. And there we have a fluxes that goes that way, that goes that way, that goes that way. Now we can map this lattice with ring onto the Karyn lattice, right? Because this point here would be this point there. Then this point there would be this point there. So now we get an exact model of a Karyn lattice of photons only. We have photons. But now the good news is the photons, they feel a flux, they feel this complex phase. And here it is done in a way that the flux, they just appear on the bow tie of this Karyn lattice. Okay? So what is really nice here, you get what you need. You can simulate some Hall effects, because you can have these fields that emerge. But now we have to be very careful here, because we get a strange lattice. And this lattice, you see, it has 3 sides, or 3 atoms per ABC, per unit cell. Therefore, it gives 3 bands. Now, with the flux, you can really control how is the shape of these 3 bands. But main point here, suppose we want to start from there. We all like here. We get Dirac fermions, right? Now we tune the flux, we open the gap, we break the time reversal symmetry. Therefore, we should be in a quantum Hall phase. And things which is nice here is to go from there to there. We can show that this band has a chain number 1. It means that if we send a photon into the gap, it would go to the edge only, okay? And do this one-dimensional motion. But now we can ask, what is the effect of this flat band? And first, what is this strange flat band? It is very hard to obtain a flat band in a time bending model, right? What does it mean, flat band? Right? What does it mean, flat band? Flat band means that we would need to have a state which is localized somewhere in our lattice. And here it comes from a very beautiful thing, which is that if we look at this flat band here, the wave function, you see, it is very magic. Here it has an amplitude plus, here minus, here plus, minus, plus, minus. Therefore, you can really localize a wave onto this ring, because the amplitude to go from there to there, or to from this ring to this point would be 0, because you get a plus amplitude and a minus amplitude phase, with the same amplitude. Therefore, there you have you are in a case where you get these states which are localized onto a ring. But main point is that these states are really so-called, I mean, you can really affect this state because it is just a magical state and it requires some very nice so-called symmetry. It means that the ABC side would have the same so-called potential. They would be equivalent. But we know quite well here, we can, so suppose we have a flat band. Now here we have at a flux here, where we can send a photon here. And we know that this state is just an edge state. Because if we just solve the bulk problem, we don't have state. This state just comes from because we solve things on the finite size sample. So we know that we can start from that flux. We can send some photon with a given energy, and for that flux, we get a quantized Hall effect. We just get one edge mode, okay, per edge of this sample. But now here, the thing which is quite weird, we get this flat band. This flat band has a chain number 0, but maybe it can do something. And yes, it can, because suppose we tune the flux, we see that this band spread. And now it means that for any impurity effect at an edge, we can scatter from edge to bulk. So here we get a non-quantized Hall effect where this spread band gives a chain number which is non-quantized. So this case is called a non-quantized anomalous Hall effect. And we can really go from one case to another and prop things in a nice way. So first we could look at simple things. We could look at the local so-called density of state. So first, for that flux here, we can send some mode at this energy here, and we can check that these modes are just localized onto a ring. Now, if we slightly change the energy, we go there, and you see that we get this beautiful edge mode. But bulk is completely gapped, okay? And now we change the flux, and we see that now we get these bands into the bulk. It means that really we can have either an edge mode or some photon state into the bulk. But now, suppose we are here. This quantum old state here is really fragile because as soon as you have so-called impurities effect, or here the disorder at junction, you see that this band will spread. And at a very general level, we can show that in a nice way. As soon as we add some impurities effect or disorder, you see that bulk, you have some state into the bulk. So here what is really nice is the disorder effect has an inverse effect as it used to be. I mean, if we start with a free wave, we have impurities, we just localize the waves, right? But here we start from a so-called localized wave. We have a little of asymmetry, and it just delocalizes the state into the bulk. So we can do many things at a general level. We could imagine we have some impurities at the edge, and for the flat band, which is perfectly flat, you see indeed that you get a mode and just go through and just turn around. Okay? But now you change the flux, and because of this band that spread in the middle, it is very simple for an edge mode to leak into the bulk. So at a very general level, when you get this kind of edge state, it is very important to check that bulk is gapped, because if not, you can really leak into the bulk. And then you lose the quantized Hall effect. Then, as I mentioned, as soon as you start with the ideal case, flat band, but you add some amount of so-called disorder, you see that again you can leak into the bulk without any impurity, just because the impurity effect or into the bulk or the disorder couple any K point to any K prime point. Then we just thought about how to measure the Chern number with, for photons, and we had a nice idea. So this will appear on the web in a few days, I hope. And some cold atoms idea, which is very close to what we thought about, just appeared as well. So here, main point is, it is nice to think in terms of this gauge field to build some nice phase of matter, but still one has to be very careful that bulk is gapped, because if not, the Chern number would be really non-so-called quantized, and you will get something which is not quantized. Okay. How much time do I have, Steve?
About 30 seconds.
30 seconds, okay. But at least that you follow these two pieces. I mean, this is the main important. So maybe I have 30 seconds, so we'll show a nice idea that, I mean, I think that this shape in 2 dimensions is a very nice array. Because you can have flat band. And flat band, it is very difficult to get flat bands. And this has a lot of application for ferromagnetism. But still, with this flat band, you can have Landau level point of view and build so-called fractional, so-called quantum Hall state. And this work by Wen, which is very nice, shows that you can really play with hopping onto the Kagome lattice and get a flat band with a Chern number which is 1. And then you really feel this band, not in a field way, but you dope this band at 1/3 level, and you could have the equivalent of a nice state of matter, a fractional quantum Hall phase. Then the so-called Kagome lattice is nice because it was one case, I mean, that has been shown to yield this beautiful phase of matter that is not a named phase. So we have a Mott state, but no named order. And from application point of view, there are many 2D compounds that show the Kagome lattice. Now, with the cold atoms, this has been built. I mean, and we hope that these groups here claim that they really see spinning photons. So since I have 10 seconds or one, maybe I can finish with this phase diagram, which has nothing to do, but because I talk about spin liquid, so I just wanted to say that now, even if we start with a Hubbard model in a 2 dimension, we know where to find a spin liquid phase. So this line is just a Hubbard model onto the Ohmic so-called lattice. And you see that at weak interaction, you get Dirac points. At large interaction, at trap filling, you get an L phase. But in between, we and this very nice group here form a spin, so-called liquid phase. So I am quite happy because it is kind of the first time that we see with a Hubbard model, a simple model, that someone could reach a new Mott phase which is not ordered. And I hope that, of course, here gaps are quite small, and with cold atom, I think it would take some time to see this phase, but still, I think it is a nice phase, and it gives some hope that we can go on and find some new things in 2 dimensions. Okay, so my time is gone. I am sorry I could not talk about that, but that's okay. I think I talked a lot already. So I will stop here, and thank you for your attention.
So are there further questions? Bill?
So I want to explore the question about the statistics again that Victor brought up. But first I want to make sure that I've understood the system that you're talking about. This, of course, is in the first part of your talk. So you have this array, and it's basically an array of cavities linked by waveguides or something.
Yes.
And in each cavity is an atom or some two-level system that the light can interact with. And if you just concentrated just on the cavity, it would just be a Jaynes-Cummings thing.
Yes.
And then then the coupling turns this into a kind of lattice and Hubbard model. So, but if I've understood, the thing that's mobile here is the photons.
Yes.
The cavities and the atoms associated with them are static. So what I'm not understanding is why, well certainly the object of interest is this polariton.
Yes.
The matter part of the polariton isn't mobile. So why does its statistics matter at all?
Okay. So at a simple level, I will try to answer that. So I would think that we see that here with just one waveguide. The way that I see that, you just couple your spin to line. And the way that I see, to me it is like to change the photons onto so-called fermions, because you have a hardcore constraint, right? Because you cannot, you can add one object, but not two. So this is somehow equivalent to add a very strong on-site repulsion.
Okay, but it in a certain sense turns bosons into fermions, but not really.
So what we have shown in our work here, you can write down this full Hamiltonian into the right basis, which means the dress-state basis, which are really this dress-state basis. And then you can build a pseudo Bose-Hubbard model. But now you see, the point is you have to keep the two plus-minus branches, because you have two kinds of dress-state, but still you can do that. And then the point is then to solve that and to look at the so-called commutation rule for these objects. And this is difficult, but at least what we can show that at simple point on the phase diagram, like here in one dimension, you can really show that those P objects become spins. They become hardcore. Then we can show only if G equals 0, you don't couple light and matter, and then you get free boson. But you are completely right. How can we solve this dress-state Hamiltonian in a very general way? This is still an open issue. And up to now, this is quite hard because we get the plus-minus branches, and we get an Hamiltonian, which is quite hard. So for the gray state, what is very nice is that the Ohmic term give the Hubbard type so-called coupling between the gray states. So it's kind of opposite to what we are used to.
In the end, is it qualitatively different from a multi-band Hubbard model? Bose-Hubbard model?
Yes, yes, but yes, you get a multi-band Hubbard model. But here the point is Ohmic term give rise to the interaction. Therefore, you can't do a simple expansion here because you start with strong interaction. So we can't use big theorem and things like that. So that's the point, which is quite hard. But you are right. We obtain a two-band Hubbard model. Yes.
Any other questions?
So you mentioned about this chemical potential as a challenge, but I may actually missed it. So what's the solution, or do you think that it's a solution? Because my feeling is that it's actually a fundamental problem. It cannot be solved. For photons.
I don't know. So with metals, you can just couple two so-called pieces of metals, and they would adapt the so-called chemical potential at the interface. So what I had in mind is that maybe someone could think about coupling this array to some kind of bus, so-called photon bus, and in a way such that the model would be very simple, and then you can integrate out this bus, and you need to show that the coupling between this bus and the array would give rise to the new term.
But that wouldn't require a very large nonlinearity. So people did this Bose-Einstein condensate of photons and define the chemical potential using this detailed balance interaction with dimolecules. But that, in these cases, that the system is very susceptible to outside work, it is hard to engineer actually those large interactions so that the photon can actually exchange energy to satisfy the detailed balance. So, do you think that it is possible to do that in a simple?
I am still thinking about that. To be honest, I just talked to the main group in that, and we still think about this idea, but you are completely right. So main idea is how can we prepare things with just one gray state in a waveguide and to make it sure that it could live a long time. So this I don't know. You have some idea, but I think right now this is the main idea. I know there are some groups that work on new ideas. You could imagine that you don't want to have a mode state, but still to have a state with a gap. And then maybe we can do that. And we can tune, but not with a mode state. And with a mode state, we need to simulate the new, or at least to prepare things to have one gray state per waveguide, I think.
So one more question.
Yeah, I'm a little confused about the relation in the Hubbard model and your model. So I sort of understand how to draw the analogy in the atomic, around the atomic limit. But what about the superfluid phase? Because then the number is not well defined. I mean, the number of photons or particles is not well defined. So how can you comment on that?
Yes, so the link between the two models is two things. First, as I mentioned, you can start with the Jaynes-Cummings lattice and write it down as a two-band model of this gray state in terms of these gray state objects. And this, you can do that. But then things become hard because we need to solve this two-band model, which is quite hard. But still, you have a mapping between the two in terms of a 5-4 theory. So in a sense, if you are very close to the phase boundary, the way that you can see the mapping between the Bose-Hubbard and this model is that they have the same field theory. So in this sense, they are very similar because they obey the same second order phase transition. So this is another way to see the link between the two. But you can't build a simple path between, or only between the mod lobes, because there I know that I can just keep the so-called minus branch, and there we can really build XX model or spin model or Bose-Hubbard model in a strong interaction. But then what is hard is how do we go to this superfluid phase? Then we have to keep the two bands, and the whole thing becomes the interaction between the states. So there it becomes difficult.
Okay, so I'd like to remind everyone that Karyn will talk with the students afterwards in the same place we just had lunch. And thanks again.